In this video, we'll be doing a left Riemann sum on the exact same region and function we were playing with in the last video. So, we're going to integrate again from 0 to 4 of the function x squared in respect to x. So we're going to find the area from 0 to 4 of this function. In that case, again, we're drawing more or less the exact same image, which looks something like this. Okay. However, in this case, we're going to go to 4, we're going to have a 2, we're going to have a 1, and then we're going to have our 0 value, and then somewhere in here we're going to have our 3. But for this one, again, we're going to use the left Riemann sums, and I'm sorry, we're using 8 intervals. So what we're going to do is we're going to have L subscript 8, and we're going to go ahead and find that by, again, adding up 8 areas. So that means I need to take this from 0 to 4 and cut it into 8 pieces. If I'm going to do that, 8 even pieces, that means I'm going to have some half values here. Well, if we're not sure how that exactly is going to pan out, again, delta x is uniform. We'll do b minus a divided by m. b is my ending point, 4. a is my starting point, 0. And n is the number of intervals I want to work with, in this case, 8. So that my delta x is actually 1/2. So that means that every interval, every new interval, will start 1/2 unit away. So that means I'm going to start at 0, then my next value is 1/2, then my next value is 1/2 plus 1/2, which is 1. Then I'm going to have 3 halves, 2, 5 halves, 3, 7 halves, and then finally 8 halves, which is 4. So these are all of the values of the endpoints of 8 intervals going from 0 to 4. So again, our delta x is 1/2, and that's going to be important in this particular case. In our last case, the areas of those rectangles weren't terribly important. Now, the second piece is I'm using the left endpoint this time, which means if I'm looking from 0 to 1/2, that's my first interval, I want to pick the left side as my endpoint. Now, this particular endpoint is going to get really unique because you'll notice we actually start at 0 as picking that endpoint. So if I'm looking at my area 1, that's going to be a sub 1 plus, again, a sub 2 plus a sub 3, and I'm going to have all the way up till I get 8 of these things. That means my left Riemann sum of 8 intervals is going to be whatever my function value at 0 is, again, that's my left endpoint that I'm picking, times 1/2, plus. In the second interval, I'm going from 1/2 to 1. And I'm picking the left endpoint. That means I'm picking this spot right here. Now I'm going to exaggerate this just a little bit so it's a little bit easier to see it, but then I'm going to go ahead and cut it back down. So again, now this right here, it's a very small rectangle, but that's my rectangle that I'm playing with. Now you'll notice the area is going to be length times width. Length times width. The width again is once more 1/2, but my length is f of my left endpoint. My left endpoint of that interval is being 1/2. So f of 1/2 times 1/2 plus. So now we have, that's 2 rectangles. I need to get 8 of these rectangles. Okay? So on my next rectangle, I'm going to go from 1 to 3 halves. I'm going to go ahead and pick the left endpoint, which is this one here. So I'm going to go up to the function, I'm going to cut across. I'm going to go up to the function, I'm going to cut across. I'm going to go ahead and finish all these rectangles so you can see it a little bit more clearly as I get further and further down the line. You'll notice every rectangle that I build is from the left endpoint over to the right endpoint. And notice that the left endpoint is the one that comes up to the function. So again, on this interval from here, 1 to 3 half, I'm going from 1 up to the function and then across. There should be a little bit of space that's not above the x-axis, but below, sorry, not above the function, but below the function. So this is going to be next, f of 0, f of 1/2. I'm going to pick this left endpoint, which is f of 1, times the 1/2, because that's the, again, width of the function. I'm going to go ahead and drop down here so I have the space. F of, well, my next intervals from 3 halves to 2, and my left endpoint from 3 halves to 2 is 3 halves, so f of 3 halves times 1/2, and hopefully you guys can recognize that there's a pattern here. I'm going to pick f of 2 times 1/2. I'm going to pick f of 2, my next one is 5 halves times 1/2. Then I'm going to go ahead and pick f of 3 times 1/2. Then f of 7 halves times 1/2. And then f of, well, let's see here, 1, 2, 3, 4, 5, 6, 7, 8. So I know I'm done here, and I shouldn't be picking 4 as an endpoint, because you'll notice from 7 halves to 4, that's the last interval, that's the last rectangle, that's a sub 8. You're going to look at 7 halves is where my function value is going to appear, not at 4. So again, this is right here my left Riemann sum of 8 intervals. I'm going to go ahead and simplify that ever so slightly such that you can recognize that it is 1/2 multiplied by all of these f function values. Number 2, it is nothing more than these function values squared, because that is the function that appears in my notation. So writing all of these pieces squared, I should be very careful about writing these 1/2 squared, plus 3 squared plus 7/2 squared. This, multiplied by 1/2, will provide me with my final result, which is not a pleasant number. I mean, we can go ahead and do it real quick. It'll end up being, let's see here, 1/4 plus 1 plus 9/4 plus 4 plus 25/4 plus 9 plus 49/4, all times the 1/2, which I'm just going to leave out there for now. So again, 1, 2, 3, 4, 5, 6, 7 pieces. If I add up all the fourths, that's 10/4 there. That's 75 minus 1, so 74. That means that it's going to be 74, 84. I have 84/4 plus 1, 10, 14. All times the 1/2, which I'm going to go ahead and simplify very quickly here. Again, adding up all these numbers. 1/2 distributed in and simplifying, I'm going to end up with, looks like 42 over 4 plus 7. And then finally looks like 21 over 2 plus 7, which I can go ahead and change to 21 over 2 plus 14 over 2, and get 35 over 2. Giving me my final result, that the area under the curve of this function from 0 to 4 is approximately 35 over 2, which, if we look back, our previous answer was 30, and that was an overestimate. And again, it was an overestimate because the area of the rectangles superseded over encompassed that graph. Now, in this example, you'll notice that my areas actually undercut the graph, which means that there's sections of space that we missed. So when this question asks, is this an over or an underestimate, we're going to call this an underestimate.